So VB, it's not. In fact, I don't even have it plugged up. So we can solve this in several different ways. Here we go. Using several different laws. But calculate VR1, we could say VR1 would be equal to 10K over 11.8K, right? Times 10. What does that give us? No, this is VR1. We'll get to VB sooner or later. We have to calculate all these resistors anyway, right? We're calculating VR1. You're talking about VR2, but we're calculating VR1, Kelly. Because y'all got to calculate all the voltage drops across all the resistors, right? It doesn't make any difference which order you do it, and we have several laws. So 10K, which would be the size of this resistor, over RT times this voltage, and what do we get? $8.5. VR2, which equals the VB, VR2 would be equal. We could use Kirchhoff's law. We could use 10 minus 8.5. That would be one way we could calculate it using Kirchhoff's law, right? Or we could use the voltage divider formula. Either way should give us the same answer. This will be 1.8 divided by 11.8. K, but the K's cancel. So what does that give me? Yeah, the K's cancel, but it's 1.8 divided by 11.8. Or you could have used this law right here. This is Kirchhoff's voltage law. It's the sums of the voltage drops in a parallel circuit have to equal to it, right? So what do we come up with here? Times 10, I'm sorry. It's laws. You could use Kirchhoff's. You could calculate VR2 and get VR1 by using Kirchhoff's law, right? You understand that? Either way you want to work it, yeah, it's fine. I mean, as long as you come up with the right answer, right? So you could calculate VR1 and then use Kirchhoff's law to calculate VR. You could calculate VR2 using the voltage divider, or you could use current. You could say IT is equal to 10 volts divided by 10K. Divided by 11.8K, and then come back and multiply the current times each resistor and get the voltage drops. So you learn several ways in DC where you could calculate the same thing. I prefer the voltage divider formula because one thing we never have to calculate current, and then you use Kirchhoff's law to calculate the other one, right? Whichever one you calculate first. It's up to you. So what do we get for VR2? 1.5 volts, yeah. And if we subtract 8.5 from 10, we get 1.5 also, right? Then we need to probably get VR4. VR4 would be 1.5 minus 0.7. So here we basically have to use Kirchhoff's law in series circuits. So what does this leave us? Millivolts. And what do we probably need to do next? Need to calculate IC. IC is equal to approximately 800 millivolts milli divided by 200. Well, it's milli. What we do when we're dealing with Ohm's law, we only use units in our answer. I mean, you can if you want to, but the problem is if you put amps over here and then you put ohms down here, then technically your votes, your answer would not be in ohms. It would be milliamps per ohm because those don't cancel out. So Ohm's law is a relationship formula. So basically, the only time you should use units in the formula is for your answer. Does that make sense? What I'm talking about? Because technically, if you put milliamps up here and you put ohms down there, then your unit should be milliamps per ohm instead of volts. But if you do it, as long as you come up with the right answer, that's fine in your answer. So what's IC going to be equal to? This is not milliamps. This is actually, so that was wrong too. This is actually millivolts. So you'd end up, your unit would be millivolts per ohm, right? So normally we don't put the units inside the equation. So what we come up with amps here? Because 800 is 4 times 200. I don't know what you mean. Yeah, so if you take 800 milli and then you divide that by 200, you should come up with 0.004. No, that's milli. That would be 8 milli. 800 milli is 0.8. Yeah. So 800 milli means I would take the decimal point and move it over 3 times, right? So that would be 800 milli. And this is why you need to get used to using that engineer notation key on your calculator, because that way you enter the units. Wait, Austin. Here's the. So Kelvin, let me see your calculator. You probably do too. I know I have it on mine. Yeah. You have to turn it sideways. Yeah, bring your calculator up and turn your phone sideways and see if all that extra stuff don't pop up there.
Oh, okay.
Yeah. So see, here's your so here's your no, it's not the EE key. So all you have to do, if you use that, you could say 800, just like it is, and then you would hit this key, right? And then you'd hit your change sign key. Where's your change? Right there. No, that didn't work. No, it didn't. Yeah, it did. And then you can divide that by 200 equals, and it comes up and gives you 4 milli. So that using that key, you can enter instead of trying to do that in your head, you can actually enter the units the way they are, right? So 4 milliamps. Then what can I do with this? I can calculate the voltage drop across R3 now, right? So VR3 would be equal to 400 milli times 1,000, 1K. Give me what? 4 volts. Now we got about everything we can need, right? So VC would be equal to 10 minus 4, which would give us what? 6. Are we okay? We've already calculated so VR2, I'm sorry, yeah, VR2, this would be equal to what? That would be VD. VC. This right here would be equal to VE, right? Okay. Okay. And so what we got to do now is calculate voltage collector to emitter. So what's on our collector? 6. What's on our emitter? 800 milli. And that should give us voltage collector to emitter. And then our voltage gain, AV, would be equal to 1,000 divided by 200. Yeah, so we'll get that means for every 1 volt we put in, we would get 5 volts peak to peak out. Is that everything? Maybe not in the right order, right? Because, yeah. So this is number 3, and they all work exactly the same way. So the only thing, new formulas that we learned is how to calculate the gain. And this is not a new formula. We learned this back in diodes, right? And all the rest of them are laws that you already know. You should already know. I didn't say you already know. I should say you should already know, right? And so hopefully what you see is this gives you a reason of all that stuff you learned back in DC. Because DC, all those resistors did was create heat, right? But here we're actually using those same formulas to bring it into an active circuit where we actually get a gain out of this thing. Any more? Well, like I said, they basically work all the same way. And you can solve it in different orders. It's up to you. So I started with R1. You could have started with R2 just as well, right? But you have to always start on which side? You have to always start over here. Because if you don't start over here, you can't get this guy on this side over here. So whichever one you stop for first is So what region are we operating this guy in? No. If it was saturated, this right here would be less than 1 volt. Yeah, if it was cut off, it would be equal to VCC. But it's not, so it's in between 1 volt and 10 volts, so this is in the active region. It is. Saturation is less than 1 volt. Well, that's not true. Cutoff VCE would equal to VCC. So if this thing was cut off, you would measure 10 volts right there. And if it's in between these two, so if it's more than 1 volt, hopefully a lot more, but less than VCC, then this is the active region. So this is saturation, this is cutoff, and this is active. So anytime I'm going to get like an amplifier, an audio amplifier, we're going to operate it in what we call the active region. And so what happens is when we bring a little input over here, let's say I bring in 1 volt peak to peak over here, which would be 1 volt. Then what over here, we would get 5 volts peak to peak, but it would be 180 degrees out of phase. If I do what? If I bring 1 volt, we would be, I can't bring in 1 volt because I've only got 10 volts to work with. That would be a +5 and a -5. We've only got 5.2 volts to work with, so it would be close to clipping it. But that's a fairly good example. And y'all understand why the input and outputs are 180 degrees out of phase, because we're taking our output across the transistor. So when the input goes positive, the transistor cuts on more, it drops less voltage, right? So this is a characteristic of what we call a common emitter. Now, when we say a common, we're not talking about the DC common, we're talking about the AC common. And if I come over here and did this, if I put my AC signal over here, if I put the symbol for my AC signal, if I moved it, is it showing up there? Is all this showing up? No, I just erased everything. Oh, maybe I didn't. Maybe I just went to the next slide. Yeah, and it shifted over. Oh my goodness. What did I do? So this is called a common emitter because the input and the output are both the common for both input and outputs are the emitter. So we'll have to look at that. Now the signal in DC, we look at current flowing from negative to positive, right? What we do in transistors is we're really not concerned with the direction or how the current flows. We're interested in how the signal flows through the circuit. So I'm bringing an AC signal in, and what you have to understand is that on an AC signal, as far as an AC signal is concerned, a DC power source is seen as a short circuit. So our signal flow, when it comes in, it would come in here, and it would split and go this way through the power source. It would split and go this way through the power source. The signal would go through here like this. So this would be the way the signal would flow through the circuit. So looking at it from what the input resistance would be, what this guy would see, Rn, it's going to be this equivalent circuit right here. We're going to ignore the capacitor, and we'd come in and we'd go to a 10K, which would be R1, right? And then it would go through a 1.8K, which would be R2. And it's going to go through the transistor, and it's going to look at this one. Now, anytime I go through the transistor, then we're going to have to use beta. And what's beta? The actual formula. It's actually IC over IB. But you're right, it's current gain of the transistor. So we're using a 3904, and its typical beta is around 100. So this is a 200 ohm over here. So my input would see this as 200 times 100. So what would it see that resistor as? Yeah, which would be the beta. And this is what we use on these was we typical beta. We know beta's got a problem, right? Using beta anytime on transistors has a problem. Why is that? Why is using beta in a math formula got problems? Why do we have to use minimum beta? Because if I looked at the beta on a 3904, it can be anywhere between 30 and 300. Yeah, because of the span. You're right. And so what we do on this one, this is definitely an approximation of trying to figure out what we call the input resistance of the amplifier. So what would the input resistance be? What's 200 times 100? 20K, yeah, good. So what I do, I would say REN would be equal to, what was the formula y'all learned in DC? 1 over 10K plus 1 over 1.8K plus 1 over 20K. Now I know my answer has got to be less than what? My 1.8K didn't show up down here, guys. I'm sorry. So what would be my input resistance to the circuit? RN. What would be the input resistance? So my AC signal is going to work into a load. And how much current's required by my AC signal is to determine what load this input of my transistor provides to it. And the way we calculate that is we put all this in like it's in parallel. So what we're doing is we're calculating the parallel resistance that this would be and this would be, but this is always time what? Times beta. Okay. And all we did was use the typical beta. So between 300 and 30, what we did is chose something that's pretty close to the center. And when we actually calculate the true beta, we're going to find out in a real circuit, we're going to find it's going to be around 80 or 90 for this transistor. So basically, I chose something about in the center. Actually, it would probably be about 115, but if we chose something exactly in the center. So what did we get for REN, guys? Anybody got it yet? You couldn't even do it in DC. It's not an easy formula, guys. All I know, and this answer looks like it might be right, because I expect it to be lower than what? The lowest resistor, which normally is R2, guys. So we can get a rough guesstimation sometimes just by using this. We just know it's going to be lower. So what would R out be equal to? Right now, R out is real easy because R out would be equal to RC. So here our output resistance for this amplifier would be 1,000 ohms. I'm sorry, yeah, 1,000 ohms.